just something to point out in case it's been missed. I'll try to remember to do this again in lab, but Trace won't be there. For things like lectures, if you want to look at the lecture slides afterward, if you go down here to lecture materials in the Moodle page and you click on OneNote Classroom for Physics, it will take you to, and it's now corrected, the link is corrected, it will take you to the OneNote. You'll have to log in with your Union College, whatever we call those things. But it will take you to where you can see all of the stuff for the class. And of course, it took me here to the physics. Notice it's in a web browser. You can also convert it to using your own laptop version of OneNote. Has the Physics 151 lectures, the Physics 251 lectures. And so you can see here the lecture I'm giving today. I'm actually going to use this for presenting the lecture today. Usually I don't use it for presenting the lecture. I'll just put them up there. And I'm not going to use the web version of it in case you're wondering. But just so you know it's there. So for instance, in homework, I know the time is now past, but we did do the calculus homework C1 on this. This is where you guys were writing last week. And so, you can come over here and while it's still loading up the PDF, you can see the work. Oh, great. Well, I screwed that up. Let's Control Z, maybe. Hopefully that fixed, undid my errors. But you can see the work that was done there. Just making sure everyone's aware of that. Okay, going to the actual presentation using the OneNote app, we're going to talk about calculus in motion. Now, we kind of did this in the first lecture when I introduced the calculus we're going to be using for this semester. But, by the way, Michael, I'm sorry I was not able to get to a computer. Yeah, okay. I had my phone, but I couldn't find the link with my phone. Okay. Anyway, sorry, no one else knows what we're talking about. We talked about kinematics. Now we're going to actually do something. We have a test, I believe, a week from today. The test will be covering chapters, for the college physics textbook 1 through 3. I know you have two schedules, and one has the university physics equivalents to the best of my determination. The stuff that is going to be possible for the calculus-based students on that first test, that you're going to have one calculus-based question to go along with the other non-calculus-based questions. Actually, I said one. I could have like some other theoretical ones as well as the problem. But the problem would be something that is either, it's going to have to use the three equations that we had last class period. That is not the first class period, for kinematics. That V is dx dt, and likewise A is dv dt. It's going to have to use one of those two equations. And it can go either way. So very quickly, let's review how we use these. Now, I have some calculus review stuff here once again, just to make sure that the terminology and language makes sense to you. In general physics, we use delta x over delta t for the definition of average speed, or average velocity as a vector. Delta x over delta t is average between the time frame of beginning time to ending time. If you want to find the instantaneous speed or velocity, all you have to do then is to shrink the delta t down to a very small value, which, as far as general physics is concerned, is impossible. But that's where Newton invented calculus and said, well, let's just take the limit as delta t approaches 0. And when we take the limit as delta t approaches 0, that's the definition of a derivative. The deltas, that's a Greek capital D, we simply replace with a lowercase d. So lowercase d means an infinitesimal change, whereas the capital delta means a finite change. So this equation, obviously this has to mean this, or we wouldn't have the equal sign between them. So the limit is delta x or delta t approaches 0, delta x over delta t is the speed. And so then likewise with acceleration was the limit as delta t approaches 0, screwed things up again, of the change in speed, actually velocity, there's got to be a way, over the change in time. So in usage, you had homework problems that used one or both of these equations. What did you do in those homework problems? What were you given?
Given either like a derivative and then it's solved for. Oh wait, it was
in the expert TA homework problem.
Oh.
Just an equation that said take the derivative of it, essentially.
Yeah, essentially. It shouldn't have said take the derivative of it because they want to make sure that you understand when it says what's the speed, that means, hey, I've got x as a function of time and I need to take the derivative to find speed. So that's one option is given x, find the speed, or given x, find the acceleration. Because if I can find the speed, then I can find the acceleration. So given x, I can find the speed first, and then from the speed, find the acceleration. So that's one way. The other way, and I know, Kaylin, you're not in calculus, but I know that they've been doing this in the calculus class, calculus 2 class, is the differential equations aspect. That's, I think, all you did the first week of calculus class pretty much was differential equations. And so with the differential equations aspect, we're going the other direction. We're going from, for instance, acceleration toward position. So I go from acceleration to speed using this equation. And first step, separate variables. Step 2 is integrate the two sides independently. Now I know in calculus 2 you've already gone beyond that to more advanced forms of how to do it, but that's the hardest we're going to do. So I know, Kaylin, you're not in calculus 2, hence you haven't gone beyond this, but everyone else has already. So we're going to work with this with some examples. Any questions before I go to, I believe the next slide is an example? Sure hope so. Look, practical example. My memory did work. So here I'm giving you not a super difficult problem, but not an easy one either. Suppose the speed is 10 t squared e to the minus 0.7 t, and I want to find the instantaneous acceleration. How do I go from speed to acceleration? Take the first derivative, exactly right. So we can do that. When is the speed the greatest? How can I find when the speed is the greatest? And I don't want you to say graphically. Graphically would be a correct answer, but that's not the one I want you to say. In calculus in general, how do you find a maximum or minimum? With no answers forthcoming, let's go to the graph, because if we answer by the graphical method, then we can bring it to calculus.
So the question is, what can we, how do we find the maximum?
Yeah.
Okay.
On a graph, how do you find the maximum or minimum? You just kind of look at it as a good answer. Look, I guess, yeah. What were you saying?
I just want the lowest and highest points on the graph.
Okay, the lowest or highest points on the graph. And what's the key to identifying, oh, this is the lowest point on the graph? In terms of slope.
And it changes to the back up, right?
Yeah, so the slope has to go to 0. And so it was like, if it's a minimum, it was a negative slope coming in and a positive slope coming out. If it's a maximum, it was a positive slope coming in and a negative slope coming out. So it's when the slope is 0 that you're at a maximum or minimum. So if we want to find when the speed is the greatest, we're going to take the derivative of speed. What do we call the derivative of speed? The ddt. What was the general name for that? acceleration. So when the acceleration is 0, that's either going to be a minimum or maximum speed. We determine which way by doing the second derivative test. And I'm going to do these things. But I just want to make sure we have the ideas in our heads before we do the practical. So when is the speed the greatest? When is the acceleration the greatest? Well, how would I find the time for greatest acceleration?
The slope is
When what?
the slope is greatest.
No, not when the slope is greatest. Actually, wait. Well, when the slope of the speed graph is the acceleration. So yes, when the slope of the speed graph is the greatest.
Yeah.
Okay. I was thinking already of the acceleration graph. What would that be on the acceleration graph?
The highest point.
The highest point, which means the slope of the acceleration is it's the highest point, 0. So to find the time what's the greatest acceleration would be to take the derivative of the acceleration, which by the way has a name, it's called the jerk. When the jerk is 0 would be when you're at the maximum or minimum acceleration. Then we have the hard one. How far does it travel in 10 seconds? How do we go from the speed to the distance traveled?
Integration.
Yeah, we have to separate variables and integrate each side independently. And this one was chosen so the separation is easy, the integral not so much. So let's do some work. And I'm afraid I just have the answers. Yeah, have the answers there. So I go off to the side to do the work. So there's my function. So I want to find first the acceleration. So using what you said, I have to find this derivative. Now at this point, you no longer are going to have to show me that you know the steps to doing a derivative or integral. The whole point of that first assignment is for you to show, yes, I can do this. Once I've seen, yes, you can do it, which I assume when I grade I will, right everybody? Then I can go on and say, okay, the person can do the calculus. I will be able to trust their outcome of calculus calculations. So dv dt, I have t squared e to the something t, which means I'm going to have to do product rule. So doing the product rule, derivative of 10t squared is 20t. And then I take the first times the derivative of the second, which is going to be and so I have, in the simplest form, I can factor out a t e to the minus 0.7t. I'm going to have 20 minus 7t. So that's the simplest way of writing the derivative. So that's my acceleration. And you notice this time I went a lot faster, didn't do all the explanation part. Next question was, at what time is it going to have maximum speed? And we look at this calculation and we can use the words you said, Vmax, when a equals 0, when the slope of v is 0. And so that gives me that. Now this is something that I'm sure you all can do, but you may very well be rusty at it. How many solutions do you see for acceleration equaling 0?
There's 20 over 7.
Okay. This here gives me equation. This equation, the acceleration is 0 when 20 minus 7t equals 0. So t is equal to 20 over 7. That's what you said, right?
Yeah.
Okay, so that's one solution, but there's more solutions.
T equals 0.
Okay, t equals 0. If you take this one right here, acceleration will be 0 when t equals 0. Should put something around this one. And there's a third one, so what would the third one be? Which part of the equation is going to have to be the third one? This one's going to have to be the third one. So I'll have e to the minus 0.7 t equals 0, which is true as t approaches infinity, because e raised to the minus infinity is 1 over infinity, or 0. And so we have 3 different solutions for acceleration to 0. There's only one correct answer, and I have 3 solutions. How do I choose?
Which one applies to the application?
Well, kind of
Which
true,
one's rational?
except 0 time is a possible real-life answer. Infinite time is not a possible real-life answer, right? You could just say very long time, and that is real life. So that is, it has a true aspect, but it's not the ultimate truth here. Trish, you gonna say something?
No, I was going to say, I was just going to exclude infinity.
You were gonna exclude infinity?
Yeah, you could do it.
Well, the mathematical test would be take the second derivative of the, the first derivative of the acceleration, the second derivative of the velocity. And if the second derivative at the time given is positive, then it's a negative. If the second derivative at the time given is a positive, as I said, I got home at 4:30 this morning. If the second derivative of the velocity is a negative value, then that means that you are at a maximum. If the second derivative is a positive value, that means you're at a minimum. So that's the mathematical way. But there is also a practical way that goes toward how Michael answered. If we take time equals 0 here, well, if you just look at the graph of the velocity function, at time equals 0, what is the velocity? It's 0 because you have t squared times something. At time equals infinity, what's the velocity? Well, e to the minus infinity is 0. Now, you might say, but it's infinity squared times 0, right? Infinity squared times 1 over infinity. Well, then we actually look at which infinity is bigger. Has anybody ever contemplated which infinity is bigger? In physics, we do. Because it's how infinity is an idea, it's not a place. In my opinion, just to make sure we're clear, heaven's the opposite. Heaven is not just an idea, it's a place. So infinity is an idea. And in physics, we're saying, well, how quickly are we getting to that idea? An exponential function is quicker than a polynomial function. And so the e to the minus 0.7t is approaching 0 faster than t squared is approaching infinity. And so, in physics, we just learned these. If you did the second derivative test, you would have had it mathematically. And so both t equals 0 and t equals infinity have a speed of 0, which is your minimum speed. So they're minimum. So that means the correct answer, the one that is the physical maximum speed, is 20 over 7. Now, of course, there had to be units involved, but my equation didn't have units, so I couldn't put the units into my answer. So we have calculated when the speed's the greatest. We haven't calculated when it's at the greatest acceleration yet. So how would I find the greatest acceleration? Amax when? Nathan said the slope of v is maximum. So when dv dt is max, right? But dv dt is a, so that was just kind of a definition. But how do we find when a is max? When dA dt is equal to 0. So if I want to find the time when I'm going to have the maximum acceleration, I need to take the derivative of this function here. So I need to take the derivative of that, which you know we're not going to do just for time's sake. We've already done one example, finding the maximum for velocity. Doing a second example of the maximum for acceleration will take longer to do and won't add any knowledge or any learning, I don't think. And then finally, we have how far does the graph go? Does it travel in 10 seconds? Now, I'm going to calculate how far it goes in 10 seconds, but first, I'm going to look at the graph. Where is the maximum speed occurring?
20 over 7.
Nathan just goes straight to the answer instead of looking at the graph. When the slope is 0, which is here somewhere, notice 3 would have been right there, so just a little under 3. 20 over 7 is 2 6/7, which I don't have my sevenths fractions in decimal form, so I'll just say 2 6/7. And so, yeah, that seems right. When is the acceleration maximum? How can you find that looking at the graph? Where the line is steepest. So if I'm looking for that steepest line, it's going to be somewhere around there. And so the answer should have come somewhere here around 1-ish. And here I have units of seconds. Let's assume the time was in, I think it said with time in seconds.
I mean, we're looking
Yeah, it doesn't.
at seconds anyway, so I would assume.
Yeah. Hey, I should have said where time is in seconds, so then you could go from there for the units. Okay, so that's how we would get those from looking at the graph. Now, how far does it travel in 10 seconds? So this graph goes out to 10 seconds. How do I find how far it traveled from the graph? This comes back to understanding calculus, not just being able to do calculus. How did I go from an equation of velocity to finding the distance? I integrated. That's right. Now, graphically, if I have the function is my y variable and the variable of integration is the x variable, the integral is the function times dx. So that's the height times a small change in width. That's area. And so an integral is very exactly calculating the area under the function. So if I want to find how far it travels going from 0 to 10, I just have to find the sum of the area under this entire graph starting at 0 and ending at 10. Whoops. I have to find that entire area. So, just as a reminder, this is probably how you first saw integration in Calculus 1. You had those little rectangles. You had to calculate the width and the height, and then you said, okay, so for my integral function, I'm going to do, and you had a lot of complicated stuff to get there. And then in the end, after you'd done all the complicated stuff, you fell back on rules for integration. But that's what you're doing in integrations. You're finding the area. So if I want to find the distance traveled, I cheated. I didn't want to do that big, long integral in class. So I did what I actually expect you to do on homework problems. You can go ahead and look up an integral if it's some complicated thing like this. That's what we really do with integrals. You know, in class, we're always about, you gotta learn to think, you gotta learn to do things yourself. And so that first calculus assignment, that's what I had to do. But in real life, if you're a practicing physicist, you don't know these integrals offhand unless you're doing them all the time. You just have an integral table, and you look up the integral table. These days, you have printed integral tables like I had in graduate school, or you can go Google it. You can go to Wolfram Alpha. That's what I did here. I went to Wolfram Alpha and said, what is the integral of a t squared e to the minus bt? In my case, a is 10, b is 0.7, and it tells me, well, here is the form of your solution, plus c. Plus c is there because I did not put limits in. If I put in limits, I'm going to take this whole function, evaluate at the upper limit, minus that function evaluated at the lower limit. If I subtract them, the constants are going to subtract away. I want to make sure all of that stuff is clear. So what I have to do then is put in my A and B, and time is equal to 10 seconds, and then subtract, putting in the A and B with time is 0. Now with time 0, it's kind of simple because it's just a e to the minus bt, well, 2a e to the minus bt over b cubed. But the upper limit is much more complicated. So once again, I'm not going to do the math, telling you how it's done, just to reiterate or remind you of what you've learned previously. Now let's go on to the practical example. A top field dragster has a peak acceleration of, and by the way, I'll point out now, in my processing of this problem, I make one intentional mistake. Just so when we get to the end and you see that there's a mistake, well, I have a slide after that saying what the mistake is. But if you see it now, you can go ahead and blurt it out. So it has a measured maximum acceleration of 5.6 Gs. Now think about that for a second, 5.6 Gs. I didn't get to the problem in my lecture, but I had a problem in the lecture I was going to work out about the space shuttle. And, oh no, maybe I did. They have the space shuttle acceleration capped at 3 Gs. And the dragsters are going maximum acceleration of 5.6 Gs. Okay, your Lindsay Force, you're driving your top field dragster. You're getting crushed when you take off from that starting line. It's not just sitting in the car. It's the proverbial, I don't know if people do this these days, but back when I was in high school, they said, you know, what's cool to do is you put a $100 bill on the dash and you say, if you can grab it, it's yours, and then you put the hammer down. The person's like, of course, I've never been in a car where anyone tried to do that. Truly, I've never been. Because there's other issues like, well, how are they keeping it there? Maybe they have a takedown because if it's just sitting there, you know what's going to happen. It's going to fly to you. It's yours. Inertia, friends. Inertia. Okay, so staying with this, we have a top acceleration of 55 meters per second squared. It's going to make it really rough on the driver. And after 1,000 feet, it reaches a top speed of 330 miles per hour or 148 meters per second. And so I'm going to model the acceleration as the acceleration is the maximum acceleration minus the speed over the maximum speed it can attain. It's a fairly reasonable approximation. So using that approximation, what's the speed as a function of time? You look at that and you're like, dude, you know, there's no time in that equation. Why are you asking me for the speed as a function of time when there's no time? Seems reasonable to question, right? But there is a hidden time. There is a hidden time because acceleration is dv dt. So if I replace acceleration with dv dt, well, now I have time. So I have that. Let's do the work. Go ahead, Kaylee.
Are we going to memorize an equation like this, or are we just supposed to somehow come up with that? Like, this equation here, is this something?
The one that I'm modeling?
Yes.
No.
Okay.
You know, you're not memorizing things like.
Okay.
Basically, in physics, we don't memorize stuff. We learn concepts, and then we apply them to problems.
We're supposed to be able to come up with that equation with the given information that we have.
Given the equation that's written in black, you should be able to come up with the equation I wrote in red.
Okay, yes, but like if on
But you don't have to come up with the equation in black.
Okay.
Yeah. Otherwise, it gets way, way too difficult. Okay, so what is the first step to solving this for, and I want to solve, what variable am I likely going to be solving for? Well,
Oh, wait, no.
I'm going to find something as a function of time. What would be fine as a function of time? V, right, because I only have two variables, V and T. So if I find it as a function of time, it's probably going to be speed. Okay, so what was the first step in solving this for speed?
Multiply dt.
Okay, I'm going to write the words first. Separate variables. Which is exactly what Michael said. Multiply by dt. And what you do to one side, you must do to the other. And so then I have dv is equal to a0, 1 minus v over v max dt. Okay, am I done separating variables? Obviously, the answer is not yes, or I would not have asked the rhetorical question. Why am I not done separating variables? I have a v on both sides. Now, once again, I'm short on sleep. My heart skipped a beat for a second there when I saw they had the v on the right side. I can't integrate v dt. And then I realized, but v's just need to be on the left. So how do I move the v to the left? Okay.
Expand. You first want to expand.
You actually don't want to expand. The reason you don't want to expand is because this thing in parentheses is multiplied by the dt. If I were to expand and try to subtract across, I would be subtracting a dt back over to the v side. So expanding is not going to lead me.
So then just divide that.
Then just divide. Divide by everything that's in the parenthesis that has the v. So now I have the equation. Now what, oh great calculus gurus? We finished the separation of variables. Are we done separating variables now? Yes. So now what? Step 2.
Calculus bit.
The fun calculus bit, otherwise known as integrate each side independently. Now I put T or V0 to V final and T0 to T final. V0 and T0 have to be at the same time. V final and T final have to be at the same time. What time is our problem going to start?
0.
We'll go ahead and start our stopwatch when the race starts. What's the speed at the instant the race starts?
0.
So our lower limits are 0 for both. That makes life a little easier. Yes?
Wait, so it's v velocity
Yeah,
final over t.
You put v final up there.
Oh, that's a T final. Wow, thanks. I do appreciate you catching my errors rather than just letting them go or saying, I don't understand. It must be right because he wrote it. Because you know it obviously wasn't right. Okay, integrals. The left-hand integral. I know one person that's done this enough that he started actually just writing the answers without having to write the intermediate steps. I personally still write the intermediate steps, so somebody's a little more fluid with this than I am right now. Right now. So what I do to make sure I don't screw it up is I let u equal 1 minus v over v max. So du is equal to minus dv over v max. Therefore, dv is equal to minus v max du. Then I can rewrite that left integral as integral of minus v max du over u Notice I didn't write the limits down. I didn't write the limits down because after I get my answer, I'm going to put back in u, and then I'm going to apply my original limits. So that's going to be minus v max natural log of u final over u initial, or more simply, well, minus v max natural log of u final, 1 minus v final over v max over 1. So there's my integral for the left-hand side. The integral for the right-hand side, every one of you should be able to blurt that one out. What's the integral for the right-hand side? Integral of constant dt is, it's just t. And so, well, I have the constant. There, I was really explicit. I wrote the 0. A aught times t final. Was it a aught all the way through? Yeah, it was. Okay. Minus a aught times 0, of course. The a aught times 0 you don't need to write because everybody knows times 0 means 0 unless it's infinite. Now I need to rearrange this. Natural log of 1 minus v final over v max is equal to minus a0 over v max t final. Get rid of the natural log by using the exponential function. That's the inverse function of natural log. So hopefully, assuming I made no errors, I don't think I did, that should be my answer for the speed v final at some time t final. Now, I only have 12 minutes left. I don't want to do the next step because the next step is harder. Well, actually harder. It's not that hard, but it takes more time. The next step is find the position as a function of time, because after all, I think I asked you to find what is the position as a function of time after we have the acceleration as a function of time and the speed as a function of time. So the speed as a function of time is, keep going down. Speed as a function of time is right there. How do I go from that to find the acceleration as a function of time? How do I go from speed to acceleration? Take the derivative with respect to time. Notice we start with an equation for acceleration, but it was acceleration as a function of speed. Now we have speed as a function of time. We take the derivative, and notice time final and v final were just at the same time. So now at this point I erase the final, and then of course it's obvious why did you have the final there to begin with, and it's because when you do the integral you cannot have the limit the same as the variable of integration. So there's my speed at any time. So if I take the derivative, actually it's not hard to take the derivative. I didn't think about this. Okay, so that should be correct equation. The acceleration is this exponential function. Starts with, at time equals 0, e to the 0 is 1, so it's going to start at a0, start maximum acceleration. And as time increases, the acceleration is dropping exponentially. And then going the other way, if I wanted to find the distance, I integrate this, and it's actually not that hard because integral of Vmax dt is just t times Vmax. And the integral of minus a0 Vmax t is going to be, you divide by the derivative of the exponent, so you divide by a0 minus a0 Vmax. And so you have Vmax squared over a0. So it actually comes out simply. And so these, well, this is the equation for position as a function of time. I didn't rewrite the equation for acceleration as a function of time. It was simple. So if that's position as a function of time, now we can test to see if our model actually works. Because we had real numbers. We had the peak acceleration, 55 meters per second squared. And we had an equation for the velocity at the end of the race and the time it takes to do the race, so we can put those numbers in. The problem here is, if you want to solve for the time when the distance is 1,000 feet, or I forgot how many meters that was, it's a transcendental equation. If you look at the equation that's below the one I have in a box, I have an exponential with time in it on the right side, and I have a linear time on the left side. There is no analytical way to solve that for time. You can't sit down with your calculator and solve it for time. The only way to do it is using like a numerical calculation or a graphical approach. And I do a graphical approach, which is actually a numerical approach, but makes it easier for me to see by graphing the calculator doing the values. So what you do is you say, let this be y as a function of time, and this be z as a function of time, and you make a graph that has both y and z plotted on the graph. So I'll put them in different colors there, and then you put time on this axis, and you find the time when the two lines cross, and that tells you the time when you're going to be, well, the time when you finish the race in this case. So here's the graphical solution. Here's what it looks like. So the left side of the equation, that's what I called y of t here, is the blue one. And the right side of the equation, the one I called z of t, is the red one. And you can see that they meet right here. So I zoomed in, and the time is right there, right about 4.184. And in fact, 4.183 is the correct answer for the fit. That's about 13% longer than the actual time for the race. Not a good answer. It also predicts that the final speed will be 116.7 meters per second. But we were given that the dragster reaches a maximum speed of 148 meters per second in that 1,000 or 1,000 foot race. How could we have improved our model? What's the error I made?
Is it within the time span that you did the calculation?
Okay, he's on the right track there. This maximum speed is not the maximum speed that dragster could theoretically reach. It's the maximum speed it reaches in this time frame. And so what I have to do is say, well, what would the correct maximum speed be for this dragster? And so through some trial and error, I determined that the theoretical speed for the maximum speed to make this work would be 304 meters per second. Yeah, that's fast. That's right. That's essentially twice the 148 meters per second. Remember, that 148 meters per second, if you go to miles per hour, which is what I gave it in, is 330. So that's, 670 miles an hour. Yeah. I mean, I don't do that on the freeway because there's other cars in the way, but obviously my car could do that. So if I model it at 304 meters per second, I get the crossover here, which then I zoomed in. So it's around here. The actual crossover time is 3.701 seconds. And the maximum speed, 304 meters per second. And it gives a final speed of 148.3 meters per second. Now that's dead on. All of those numbers match, which means this model seems pretty reasonable, that the acceleration really is proportional to 1 minus the speed over its maximum attainable speed. So what we've done here is a very practical problem. We used calculus and we used a real set of numbers to find what the ultimate speed of the dragster in theory would be. Now I say that's its ultimate speed in theory because you have things like, you shift gears. It's not a single gear for the dragster. And the power and torque, those are numbers that change as it's going through the race. And this was assuming constants for everything. But it still gives you a really good prediction. So what we've done in this problem, now, on the test, you're going to be given a problem like this? No, it's too complicated. But what you will have to do is take an equation that's either position, velocity, or acceleration, and it'll be as a function of time. I won't give you acceleration as a function of speed because it throws into one extra complicated step. But you will have to take that and go to either acceleration, velocity, or speed, or position from the starting equation. So you need to be comfortable going either direction with those equations. Questions?
Yeah, so basically, the equations, when we're doing like velocity, we'll be taking derivatives of those just to calculate time. Like if you look for acceleration, we'll be doing that.
Okay, so if you're given velocity and I ask you for acceleration, then you're going to say, aha, acceleration is dv dt, do it. If I give you velocity and I ask you for position, you'll say, aha. Velocity is dx dt, so dx dt is equal to this equation you gave me. Now I have to separate variables, then I have to integrate both sides, and now I have an equation for position as a function of time.
Okay.
And that's really 2 of the 4 options you have. The other 2 options would be, I give you position and I ask you for velocity or acceleration. Fundamentally the same thing, just 1 step versus 2. Or I give you acceleration and ask you for position. 2 steps again instead of 1. Other questions? Alrighty then. Let us adjourn 2 minutes early, and I'll see you back for laboratory.